Okay, there's something wrong with the projector, and it seems that the dual mode doesn't work. I can only turn on this one single projector. Okay, for those people online, can you see the screen? And do you have the sound? Obviously, okay. All right. Okay, I think this screen is big enough for this classroom. Can you see that? Yeah? Okay. All right, let's continue on from previous lecture. I just had like one particular example I didn't quite finish. Let's finish the example, and then we'll look at some applications of triple integrals. If you got time, so we'll go into another topic, basically called vector field. All right, so let's finish that example. So this is an example I started. You have a region D, which is sandwiched by these red edges. Okay, this region D, basically region D, one side is the cylinder, the other side is this spherical surface, and then three other sides are the coordinate planes. Okay. The question asking for the volume of this region D. So this one is a little bit tricky because the way how you can find the limits. Volume of D, basically you're looking for just this expression, triple integral D dV. And because one of the surface is spherical surface, so chances are you should use spherical coordinates. Spherical coordinates is rho phi theta. So the formula for spherical coordinates is rho sine phi d rho d phi and d theta. All right, so then the next logic step is to find the limits for rho and phi and theta. Okay. Now we said in a typical approach is you sketch the region D, which we already have it. And the next step, you should also sketch the shadow of the region D in XY plane, which is already given it here. So that's that little section of area in the XY plane. Okay, so you need that to identify the theta range. So first step to identify the rho limit. For rho limit, what you do is, right, you start from the origin, then you draw an arrow line, okay, out of this region D, okay, cross this region D. So this reading line is drawn to cross the region D. So there will be a first contact over here and then another contact on the surface, on the outer surface. So that's how you find the limits. First contact give you rho mean and second contact give you rho max. Right? So how we find the rho mean, rho max we said is pretty simple because rho max is right on the outside surface, which basically means the rho max is A, right? So rho max must be A. So it's the rho mean takes a little bit of effort. Rho mean is this much distance from origin to the first contact. So we said what you could do is, right, you can look at this cross section. So you draw a cross section like that. Okay. So this cross section we're talking about here, okay? And this section is the section inside the region D. Okay. So then you can just draw the cross section out, okay, like this. Okay. And this z-axis is right here. And whatever this axis is this line over here, right? Because the inside is cylinder, so this portion is B as given by the sketch. Okay. So the reading line that you have just drawn here is is this one. This is the reading line inside this 3D space. Okay. So row mean is from here to here, right? So this is your row mean. Okay. Row max is from here to here, which you already said is 8. So now you look at the row mean at here. Right? How do I find the row mean, an expression for the row mean? The other thing you need to write it down is, right, from the z-axis to where the reading line is sketched, okay, this is the definition of your phi angle. Okay, so if this is a phi angle, so then we can look at these right triangles right here. So that right triangle, so let's draw the right triangles right here. So this is right triangle, this is a phi, this is a b, okay, and this side is the row mean you're looking for. So apparently row mean equal to b over sine phi, right? Because row mean times sine phi equal to b. So b row mean is b over sine phi. And that's how you can label your row mean at here as b over sine phi. Okay, so this is the tricky part to find the row mean like that. Okay. Second limit is the limit for the phi. Okay. So this is basically the reading line that you sketched, right? What will be the limit for the phi? I can continue to use this cross section as a demonstration here. So apparently your phi, right, is what you do is, as we said, you rotate that reading line, okay, and then find the edges, okay, depending on the given region D. So if you look at the current cross section, so one edge must be over here, and the other edge must be over here. Okay, and that's your phi limit. So phi max, that's easy. So for this edge, the phi angle is what, from z-axis to over here. So it got to be pi over 2, right? So that's easy. Now this one, the phi mean refer to the angle from here, to this edge, right? That's the phi mean. So let me re-sketch this phi mean, right, to have a better understanding here. So let's just re-sketch this cross section here. All right, so this is your phi mean. Okay, yeah, and this is your B out of here, right? So we need to find the angle corresponding to this edge. So we make use of, again, we need to make use of the given condition. So B is over here. So if I look at this right triangle, what is the length from here to here? What is the length from here to this edge? A, exactly, right? Because that point is on the surface of the sphere with radius of A. So this hypotenuse at here is A. Okay. So then use a simple to this. If this is phi mean, this must be phi mean too, right? So now it has a sine phi mean equal to B over A. Then if you have the number for B over A, of course, you can calculate the inverse of the sine. So you get sine inverse or arc sine B over A. So this is where you put it over here, right? The minimum value limits for the phi is arc sine, it's a little bit small space. So arc sine B over A, okay, for the phi. Is that clear? Yeah. So last step, theta limits. Theta limits is you look at this shadow over here, you draw a reading line out of the shadow, and then you sweep starting from the x-axis and sweep across the shadow and find the two edges that sandwich the shadow. Obviously, the first one is over here, the second one is on the y-axis. So your theta limits should be 0 to pi over 2. Now this concludes the setup for this triple integral for this particular region. Okay. So I would call this as sort of a trickier type of a triple integral in spherical coordinates, because you're required to, it's not that straightforward to immediately identify the minimum or maximum limits for the integrals. Okay. But you just have to make use of the available conditions. Most of the time, make use of the triangle, right triangle relationship to figure out an expression for the limit. Okay, I will leave that calculation to you to find the actual value of the volume. Okay. So let's take a look at triple integral applications of a triple integral. Right. So if you recall that when we finished the double integral, we spent a lecture or two on applications of a double integral, and we illustrated quite a few different applications, right? But one of the constraints for applications of a double integral is that because it's not really a 3D object, so it's about a thin plate, or it's about a cross-section area. Okay. So now we learn triple integral, and triple integral is about integrate over a 3D region D. So now we can actually extend the applications to more real-time applications. Okay. Number one, you can calculate the mass of a 3D object. So most of the results I'm writing down here, so I'm not going to rederive anymore, because the difference is only basically just add one more integral, right, compared to the double integral. So let's say I have an object represented by the region D. So this is a 3D object, and we can let delta x, y, z be the density. And meaning if you pick a point from inside this object and you plug it into this function, delta function, then you get certain density associated with that point. Okay. And then, apologize. Okay. And then the mass, okay, is basically equal to, you integrate the density over the region D, and you get the total mass. So what this term in here, right, what this delta x, y, z times dv does is essentially if you pick a very small box, okay, around, okay, a certain location, and the density multiplied by the delta V give you a small mass over the area, right? When you add up all the small area mass, small box mass, then you get a total mass, right? That's what you get over here. So, okay, so this is called the mass of a 3D object, the first application. Okay, first application. Second application, right, is called average value of a function, okay, in region D. Same thing, it's just from different perspective. So if I redraw the region D at here, okay, if this is region D, and then you have a function f, okay, defined over this region D. So you pick a point in the region, you plug it in here, you got a value. You pick a different point, you plug it here, you got another value, right? So then the question is, what would be the average value, okay, within this region D for this function f? Okay. If you look at the formula we derived for the double integral, okay, in that formula it says it's 1 over the area, but this time, right, it basically becomes 1 over the volume of this region D, and then multiply by the integral of this f over the region D. The only difference is we added one integral here, and then this one, the denominator, instead of it's the area of a certain thin plate, it becomes the volume of this region D. So this way you will get the average value of this function f. So for example, function f may be represent a temperature. So if you have you have a classroom here, this is region D, and at each location within the classroom, you have a temperature. So what would be the average temperature within this classroom? What do? Essentially, you use this formula to calculate the average value. Okay. An extension of this application is the weighted average. Right, the weighted average. Now, weighted average means, how do you weight this function f? Okay. The difference, so if I still use f, let's call it f weighted value. Okay. So this time is 1 over the mass of D. Now, maybe I write it down here. Let's weighted average. I'm going to use the density. Okay. For example, if I try to use the density function as the weight, okay, this function delta as the weight. Okay. So the function for the weighted average is you integrate f x y z and then times delta x y z dv. So this one serves as basically as the weight. Okay. You're weighting this f with a little bit of mass at here. Then you can get the weighted average by divide this total mass of this region D, or the 3D object. So if you compare the formula for the double integral weighted average, the difference is you added an integral here, and also instead of a mass of a thin plate, this is a mass of that 3D object D. And that's the difference. All right, and the next is center of mass. So because you have a 3D object, then the center mass will have basically X, Y, Z, 3 components. This is pretty straightforward. You make use of this formula for the weighted average formula, and all you need to do is you change this function f with x. Then you can get the center of mass of the x component. Okay. Similarly, you can get the components y and z. It's pretty much the same thing, except this is y at here. Everywhere else is the same. Okay, yeah. So I'm going to let you to write down the z. It's exactly the same. Just change the y to z. That's center of mass for a 3D object whose density is defined by delta. Right? That's the formula. Okay. The last one, which is actually, I want to give you an example. Okay, and as you can see, all of the formula involved over here for the applications. They're really nothing new. You have a triple integral here for the mass of a D, and you have this triple integral over here, right? It's all regular triple integral calculation, and there's nothing new, except you're putting together, then you get a new meaning, right? And then application. And the other important application is moment inertia. Now this is actually the true moment inertia now, because you're talking about 3D object, and we're talking about moment inertia, and moment inertia is always about a rotational axis, right? Okay. So moment inertia about this rotational axis, x-axis, y-axis, or z-axis, or an arbitrary rotational axis. Then that can be true too. The general formula of moment inertia, okay, is you pick a point, okay, and then you calculate the distance look at the distance from the point to the rotational axis, okay? Then you square it, okay? You square it. So this is the distance from that point to certain rotational axis. Then you multiply by the small mass associated at the location. So small mass given by density times a small volume at the location, right? So this is basically give you, if you recall, that give you a mass moment, right? So this little guy here represents a small mass or infinitesimal mass in this case. And then times the distance from that location to the rotational axis squared. Okay. After that, you integrate over the whole region D. Then you get this moment inertia about that rotation axis. Okay. This is a general formula for calculating a moment inertia about a certain axis. In our case, what we probably more interested in is a few moment inertia, okay, about an XYZ axis. Okay. So for example, let's see, what is the moment inertia of the 3D object about the Z axis and consequently also the X axis and Y axis. So I can apply this formula here. Okay? I can apply the formula to the application of moment inertia about the Z axis. Okay? So according to this formula, okay, so about Z axis, so essentially it's like this. You have a 3D object, okay, and this is your Z axis. Okay, then how much of a rotation, right, can be initiated, or how difficult to make it rotate around this Z axis. And that's what we call the moment inertia about a Z axis. So if you pick a point, right, if you pick a point and you look at, then what is the distance from that point to the Z axis? And this is where you insert over here into the bracket. Okay. For any point, its coordinate is X, Y, Z, and the distance from here to the Z axis is X squared plus Y squared. And then you squared it, right? Squared it, and then times the density dV. Right? That will be your moment inertia of this object about the Z axis. So this can be simplified easily because square root is squared, and then you get rid of the square root. So then I'm gonna just write it down as X squared plus Y squared. And we call this as IZ. So when you have a moment inertia with a subscript Z, that indicates this is the moment inertia about the Z axis. Okay. All right, so similarly, you can get IX IY okay. So moment inertia about the x-axis and moment inertia about the y-axis. So these three serve as a quite an important quantity for any object in 3D space. Okay, so you calculate the moment inertia about each one of the special axes. Often in time, you actually can make use of the results to obtain the moment inertia about some other axis. Okay, yeah. In mechanics, you have a so-called inertia tensor matrix. So that in moment inertia tensor matrix will contain Ix, Iy, Iz, and also Ixy, Ixz, and Yz. So anyway, sorry, that's a different topic. Okay. Yeah. Okay, so those are the formulas, okay, involved for applications of a triple integral. Okay. Again, they're a natural extension from double integral, applicating double integral to triple integral. If you look at each one of the formula, right, there's nothing new there. They're just basically triple integral needs to be calculated. Okay, so let's take a look at an example together. Well, I'll look at an example of a moment inertia example here. Okay. So let's consider a solid, okay, given by this region D. Okay. And the region D has a boundary of two surfaces. So region D is bounded by a surface z equal to b. Another one is z equal to a times square root x squared plus y squared. So obviously you can immediately tell, so z equal to b is a plane, and z equal to a times x squared plus y squared, that would be a cone, right? So you can draw an illustration of this region D. At top is the plane z equal to b. And the side is the cone a square root x squared plus y squared. And I'm required to calculate this moment inertia about the z-axis for this cone. And also consider, let's assume the density for this object is a constant 1. Okay, so make it a little bit simpler. So uniform distributed density, and it's 1. Okay. So then you calculate IZ. So first step, you write down the formula for the IZ. It doesn't matter what kind of object. Your IZ is x squared plus y squared, and then times delta function dv. And because delta is 1, so now you are left with just x squared plus y squared dv. Okay. Second step, okay, is to calculate the triple integral. And to calculate the triple integral, this is where you're going to have to make a decision. You have 3 different coordinate systems you can make use of. You could use either Cartesian, cylindrical, or spherical. Now, this one doesn't really have any spherical surface involved. So if you remember for cone, actually you could use spherical, but let's choose the cylindrical for the cone surface out here. Okay, yeah. So I'm going to choose cylindrical. That basically means your x, y, z, if you recall, x equal to r cosine theta, y equal to r sine theta, and z is still z, right? Yeah. And then the whole formula out here, the IZ. Okay. First of all, you replace the x with r cosine, y with r sine. Okay, so r squared cosine theta squared plus r squared sine theta squared. Okay. And dv, and that will be r dz, dr, and d theta. Right. And the order of integration, if you recall, I have already recommended that you should integrate with respect to z first, then dr and d theta. Okay. All right. The region not going to change. It's still this region, basically. Okay. The drawing inside this 3D is still going to be this region. However, you need to find the limits for z, r theta. In particular for r theta, if you recall, because it's cylindrical, so I need to obtain the shadow of this cone or the region D or the solid in the xy plane. Okay, so we need the shadow to figure out the r limits and the theta limits. Okay, so there are a number of things going to happen next is that you have to figure out the limits, right? First of all, simplify the term inside the bracket, and that becomes r squared, and then times r, which is r cubed. So we'll just write r cubed here. So dz, dr, d theta. So I have the limits need to figure out at here. Okay. So first, let's figure out the limits for the z. Okay. So the steps we figure out the limits is you pick a point inside the shadow, then you draw an arrow line, okay, in the positive z-axis direction. The first contact give you the z mean, and second contact give you the z max. Let's do the easy one. The Z max is always on the top surface, so Z max must be B. Okay. Z mean falls onto the cone surface. Right. So then what will be the Z mean? The cone surface is this. So technically, your Z mean is A root x squared plus y squared, right? Yeah. However, I'm not using Cartesian coordinates. I'm using cylindrical coordinates. So I just have to replace the x at here with r cosine theta, replace the y with r sine theta, which you end up with just A times r. Okay. So that results, I believe we have derived when we're learning cylindrical coordinates. So the Z limits for the mean, for the minimum limits for the integral is A times r. Good. So that's your Z limits. Next step is to find the theta and r limits. So that is determined by the shadow, right, for this region D in XY plane. So you draw an arrow line out of this shadow. R mean is 0, R max falls onto the outer edge of the shadow. And so then R mean 0. So now you do need an equation for this shadow here. So now you go back to this, where is the shadow from? The shadow from the cross section of the top plane and this cone surface. Basically comes from the intersection of these two surfaces. So the intersection means at this intersected curve, both of Z values are the same. So this intersection essentially give you what? A B equal to A root x squared plus y squared. So you're letting the two expressions the same. And then you can solve, you get x squared plus y squared equal to B over A squared. And that's your shadow curve, which is a circle, right? And the circle has a radius of B over A. Then your R max must be B over A. So you nail down the R max now. The next step is the theta limits. So rotate this whole thing. Yeah, and if you have a full circle, so theta must be from 0 to 2 pi. This concludes the three limits for dz, dr, and d theta. Okay? And then the rest of the work is to calculate this carefully, right, to find the right value. So let's try this together here. Okay, this is actually one of the final exam questions, exactly coming from the lecture notes. Okay, and not everybody got that actually. So anyway. So let's try this together. First integral is about the z. Okay, the first integral is not about r, huh? It's about z. So you get b minus ar times r to the power 3, and then dr d theta. Okay. And second integral is about r. So that you should have 1/4 r to the power 4 times b minus 1/5 a times r to the power 5. Then you plug in r limits from 0 to b over a d theta. Okay. So the results of this calculation has nothing to do with theta. So theta goes from pi over 2. So basically you get 2 pi multiplied by whatever this, you plug in the limits b over a into r, and then plug in 0 into this r here, right? So you should get 2 pi times 1/4 b to the power 5, a to the power 4 minus 1 over 5, b to the power 5 over a to the power 4. And then a little bit of simplification, you get 2 pi, you get pi b to the power 5 over 10 times b to the power 4, a to the power 4. Okay, this is the moment inertia of this particular type of this particular shape of region about the z-axis. Okay. So those are basically what I wanted to cover about applications of triple integral. Okay. As you can clearly see, as long as you know which formula to use for that particular application, and the rest of the work, right, has nothing new added to it. It's all about choosing the right coordinates and calculate the triple integral carefully, okay, and you get a certain number. Okay. Any questions on triple integral applications? Good. All right. So we've done quite a bit of integrations. Okay, double integral and triple integral, right? We have before that we have multivariable function derivatives or calculus. Okay, so from here up to the end of this term, so we're going to focus back onto vector fields. Okay. And one of the things I always wanted to see from now on is, if you recall from the first lecture of this term, and I have said the highlight of this course pretty much happens in the last 2 or 3 weeks. Basically, that's what we're gonna look at. Why is it the last 2 or 3 weeks are sort of the most important part of this course? Everything we learned before now will actually be used together, especially in the last maybe 2 or 3 or 4 lectures. Okay, so just keep that in mind, and you'll see how things are being integrated together, okay, to solve for certain, mainly 2 or 3 theorems. Okay. And they all happens within the vector fields. Okay. So first, let's look at what is a vector field, okay, and what does a typical vector field look like if you have the function. Right. So first thing is, don't think of a vector field as something new. It's actually not new because we have learned vector functions. So for example, if I have a 3D, in 3D, I can construct a function. I call it a vector function. And it's a function and it has 3 components. And each component is a function of x, y, z, scalar function. M and P. Okay. Now that is a 3D vector function. Because you look at each component of the vector, they are a scalar function of x, y, z. Okay. And similarly, you can construct a 2D vector function. In this case, there are only 2 components, but each one of the component is a multivariable function of x and y. Okay. And we will focus mainly maximum to 3D function. Okay, yeah. Then what is a vector field then? Okay. So vector field is basically just a cluster of vectors, okay, based on the given vector function. Okay. That's essentially what a vector field is. I'll show you a couple examples, and we'll see it's actually nothing we have never seen before. We just now describing it a little bit different. Okay, let's say I have a vector function like this. F equal to x I hat plus y j hat. So I'm going to demonstrate how a vector field can be constructed using this vector function. So first, I'm going to use a point. Let's see, plugging a point x equal to 1 and y equal to 1. So then this vector function give me I hat plus j hat, or just write it as 1, 1 like that. And if you plug in 2, 2, you get 2i hat, 2j hat, or just 2, 2. If you plug in -1, -1, so you end up with -1, -1. So whenever you plug in, basically whenever you're plugging a pair of coordinates into the vector function, and you end up with a vector. So now what we're going to do is we're going to sketch these vectors, okay, all of the vectors into the XY plane. So here's how you sketch. So you have a 1, 1. So you go to the 1, 1 location. Okay, so this is 1, this is 1. Then you sketch this 1, 1 vector, okay, starting from the 1, 1. So technically, what is a 1, 1 vector? 1, 1 vector is you create it from origin to 1, 1. That's your 1, 1 vector. But now we're not sketching this 1 vector starting from origin. We actually sketch it starting from 1, 1. Okay, that's where the X, Y, Z coordinates are. So you get the vectors attached to 1, 1. And similarly for a vector at the 2, 2, and you do this exactly same thing, then you sketch a vector 2, 2 and attach it to the location 2, 2. But this time, because this is a vector 2, 2, a precision drawing is not necessarily have to be that precise. So 2, 2 is a vector must be what? Longer than 1, 1. But of course, 2, 2 and 1, 1 pointing in the same direction. So you need to draw a little bit longer vector, okay, attached to the 2, 2 location. And similarly, you can do exactly the same thing at 1, -1, -1 location, and then you get a vector pointing this way, right? So I'm only drawing those 3 out of here, but if you can imagine, I mean, so basically if you draw as many as possible, okay, so technically what you end up with a whole bunch of vectors pointing outwards, and the further away from the origin, the magnitude of the vector will be getting bigger and bigger. So you end up basically what we call vector field, right? So let me show you the pictures, what it looks like, a computer generated graph. So this is computer generated. So you have a whole bunch of radial, this is called a radial field, right? The far away from the origin, you get a larger and larger vector magnitude. Okay. So this is called a vector field, right? So you can see vector field is a direct result of a vector function. And in this case, it's a 2D vector function. Just bearing in mind of how each vector is generated and how the vector is attached to, right? So that's how you generate vectors. So let's take a look at another type of vector function. Okay. So let's say this is another one in here. So yi hat minus xj hat. So if you want to manually sketch this, you can do the exactly same thing. Plugging a coordinates 1, 1. Then you end up with a vector 1, -1. If you plug in a vector 2, 2, then you end up with a vector 2, -2. Okay, so then you can sketch these vectors within XY plane by following the same procedure. First, find the 1, 1 location, and then attach this 1, -1 vector to this location. So what is 1, -1 vector? 1, -1 vector technically is a vector from here to here, right? So that's 1, -1 vector. But I'm not sketching it here, I'm sketching it over here. So you should have this vector attached to this way. And similarly for the 2 and 2 location, you have a vector 2, -2. And so that's attached to this location, but it's a longer magnitude. So that you get the other 2 vector, okay? So the more you sketch, and then you end up with this vector field. And when you sketch them out, as you can clearly see, right, this is a spin field. It's like a water flowing, right, within this 2D field. And the far away from the origin and the faster flow of the water. Okay? Yeah. Okay. Now, for your interest, you can try just add a sign, right? Just add a negative sign in front of this previous vector field. If you put a negative sign, this become negative y and this become positive y, then the vector field you will see will just simply change its direction. Okay, yeah. So those are examples of vector field. And this is an example of a 3D vector field. Now this vector field is a result of the gradient calculation. So let's take a look at this quickly. If I have a surface given by x squared plus y squared plus z squared equal to 4, I can calculate this gradient vector, which turned out to be 2x, 2y, 2z. And then if you sketch this vector field, then you can end up with like a porcupine needles pointing all the way outward radially, and the far away from this origin, the bigger the vector magnitude it is. Okay. Vector field is also very useful. This is an example. If you have airfoil and you want to study the aerodynamics of the airfoil, so what you do is you place it in the wind tunnel and then you blow smokes into the wind tunnel, and you can look at essentially the velocity of the wind across this cross section of this airfoil, right? And that gives you some sense of how good of design your airfoil is. And there are many other applications of vector fields. One of these is temperature. So if you look at the temperature distribution or wind distribution over a certain area, they also use vector field to indicate that. So anyway, I'll stop here. What will happen next is we're going to do a lot of things within a vector field. We'll do integrations over vector fields, okay, mostly. Okay? All right, so have a good weekend. Just a reminder, the quiz is happening. Now, this time the quiz will be slightly different from previous quiz. It will be a multiple choice quiz. And on top of that, I'm also giving out assignment number 7. Assignment number 7, and I used also slightly different format. Okay, it's called a web work. I have a very short description of how to use the web work on Canvas. So take a look at it. You have unlimited try. So don't worry if you make a mistake, just try again. You just have to punch in a number. And maybe as close to the final, I will also give you another set of assignments 7. It's just for some additional exercise. Okay, so let me know if you experience any problems with the web work, because I find it's new. It's also new to me, right? Yeah, thank you very much.